Awesome. Good afternoon, everyone. I'm joining y'all from the great city of New York, technically Teaneck, New Jersey. But we're part of the Tri-City area, and we have a snowstorm today. So that is fun to be here. Children in the background, that is why. And so I have the pleasure of introducing Dr. Ndao. And my name is Adelis Pollard. I'm the Director of Research at one of the city and universities of New York, Borough of Manhattan Community College. Professor Abdoulaye Ndao is an assistant professor of electrical and computer engineering at UCSD, or University of California in San Diego. And he now heads his lab, the Ndao Lab. I just had to throw this in because I love the acronym. So Nano Devices and Applied Optics Lab, which is dedicated to multidisciplinary and interdisciplinary approaches that bridge research across disciplines, especially in the areas of fundamental science, nanophotonics, integrated optics, nanomaterial structure design, biophotonics, and prototype device development in both passive and active devices. He was previously a postdoc researcher at UCSD and UC Berkeley, as well as an assistant professor at Boston University. He received his master and PhD degree in physics from the University of Franche-Comté in France. And Dr. Ndao is a recipient of 10 prestigious awards, included Sculpted Light, In the Brain Innovation Award, Skylog, Advancing Bioimaging Award, Boston University Outstanding Faculty Committee Service Award, Friday Family Career Development Professorship, the very best young researcher at Boston University, Top 10 2021 Rising Stars of Light, Top 10 Breakthrough by Physics World, Triton Innovation Challenge Grand Prize winner for LiDAR applications, prize winner of Institute for the Global Entrepreneur at UC San Diego, to name a few. Very impressive catalog. His research interests span wide-ranging topics in photonics, material sciences, and physics. So join me with introducing and having Dr. Ndao here today.
All right, thank you very much for the kind introduction and for giving me the opportunities to present my work today. Can you hear me well? Yes?
Yes, we can hear you great. Thank you.
All right, so today I would like to talk about symmetry and topology in photonic nanostructures. My talk today will be maybe a little bit different to previous talks because it will be focused more on the physics and then the applications that can come out of the physics. So I will talk about 3 different aspects today, which is the laser, a detector, and a lens. All of them can be used for imaging. So as we all know, in the recent years, the demand of miniaturization and integration is of a great interest, especially the devices that we are using in our daily lives, such as GPS, cell phone, and so on. So as an example, I would like to show the new cell phone here. Sorry, I just want to use the pointer. I would like to show the new cell phone where in a very tiny space you have multiple functions. So in order to satisfy such high demand, new integrated optical devices must be compact, highly efficient, multi-frequency band operation, and so on. So in this perspective, we show for the first time a new type of laser that we call topological laser. This laser can have arbitrary shape, which means that you can densely pack them on chip without losing any functionalities. It is one-way propagation. As we know, any lasers that we will buy now, you always have an isolator to avoid backscattering of the light in your system. But this laser itself is self-isolated, which means that you can reduce the number of elements that you will put on chip, which will make it more compact. The second part will be dedicated to singularities in non-Hermitian system, where we show a new type of optical sensor that can detect a very low concentration up to 300 times better than the state of the art. And then I will finish by presenting a new metalens that can go from the visible to the IR. So we call it octave bandwidth achromatic metalens. So this lens can be used either in the visible or IR or at the same time. And it had the highest efficiency as a metalens to date in this literature. So I will start now for topological laser. So just a brief definition and explain people the physics behind. So what is topological insulator? So imagine you have insulator material here with given conduction band, valence band, and band gap. If you take free electrons within the band gap, you will not propagate in any direction because you are in the gap region. However, if you have a bulk material and you apply magnetic field, they will start to circulate in same direction with the same cyclotron frequency. Even so, you are in a condition band and valence band, again, it will not propagate in any direction because of that. But now, if you look at here, right at the boundary, what you will see is you can see some semicircle. What does this mean? This means that if you take free electrons that you put right at the boundary, they will start to propagate in forward direction regardless of the shape of the boundary, which means that you will have forward propagation of your light regardless of the shape, and you will not have a backward propagation of the light. So all the history I just mentioned here are based on fermionic system, but it was demonstrated recently that under specific condition, under specific characteristic, such as breaking time reversal symmetry, breaking spatial symmetry, some of the fermionic system can be transferred to bosonic system. And this was a Nobel Prize in 2016. This is just to give you a little bit history of what I would like to talk about today. So topological insulator was demonstrated in different frequency range from acoustic to microwave in optics recently using either ring resonator or spiral structure to create artificial gauge field. But all the work I show here and any other work in the literature try to show the robustness of topological insulator. So the question that we ask ourselves is, can we use the physics of topological insulator to make a real devices? So how we did that is we proposed a new platform where we combine multiple material as you mentioned at the beginning. So I'm doing different optics, photonics, material science as well. So we combine different type of material here. We have multi-quantum well, we have deuterium, iron, garnet, so different material with different functionalities. So the green material that we have here is a gain material that can give a lasing because you have a gain. And we have on the bottom substrate, we have what we call deuterium, iron, garnet, which is a magnetic material that can break the time reversal symmetry. So the proposed structure is a hybrid structure. So we have two types of photonic crystal, which is two types of shape of periodic structure, where we have inside what we call non-trivial photonic crystal and trivial photonic crystal outside. And right at the boundary, we can have edge state, as I explained before. So what differentiates the two photonic crystal here in a very simple way is, let's consider two types of shape. We have the orange and the donut. In order to go from orange to donut, you need to add material in here, or if you want to go from orange to donut, you need to punch a hole. So this transition, phase transition, is what we call Chern number, and the value of that Chern number will determine the characteristic of the photonic crystal that we will use. I mentioned at the beginning in my talk here that if you have n equals 0, which is as if like the orange because there is no holes, and you have on the other side n equal 1, that means you have a hole. So right at the boundary, you can have edge state and the light can be guided there. So this is the physics that we will use to demonstrate the first topological laser. So how we design it, just to give you an overview, we use a air-hole-shaped photonic crystal, and we look at the band diagram of the photonic crystal, and we calculate what I just talked about, the phase transition, which is the Chern number, and it as if here, after calculation, the value is 0, which means that we have a trivial photonic crystal. And then we did it for the star-shaped photonic crystal, which is the photonic crystal of the cavity. And we have a very narrow band gap when we apply magnetic field, and the Chern number is 1, which means that we have no trivial photonic crystal. So now, in order to make the laser, we want to have lasing around 1.55, which is the telecom wavelengths. So what we did is we designed the two photonic crystal in the way that their small band gaps that we have here will overlap around 1.55. And then we put a point source right at the boundary, you have photonic crystal A and photonic crystal B, and right at the boundary, you have a point source. When you apply magnetic field, you can see that the light is propagating in forward direction. And when you flip the sign of the magnetic field, the light will go in the opposite direction. So we show we can successfully design a device that can have edge state and can be used for a laser. So next step is the nanofabrication, which is another step in my work. We have to design the structure, we have to do nanofabrication, and then do the characterization. So this is the device that I show. We just simulate using console. And then what we did here is the nanofabrication, which consists of three main steps. We have e-beam lithography to define the shape of the nanostructure. And then we have etching, where we remove the material, and then we have to bond it in a magnetic material so that we can have, we can show the effect of the lasing. And then we have to characterize the system after successfully fabricating it. You see that the shape looks exactly the ways that we predicted in simulation. So in order to characterize such system, what we did is we uniformly pump these optical devices using another laser. And the first things that we did is we don't use external magnetic field. What will happen is we don't see any lasing at the edge of the device. And then we apply magnetic field. We can clearly see there is edge state and the light is emitting out. But to make sure that such edge state correspond to the lasing action, what we did is we look at how the pump power as function of the emission power. And you can see here, which is a characteristic of lasing, we have from spontaneous emission to the lasing action, which show for the first time that we can have topological laser using magnetic material to break time reverse asymmetry. But I mentioned at the beginning of the presentation that this laser is one-way propagation. To verify such a one-way propagation, what we did is we collect the light at the edge of this waveguide and we flip the sign of the magnetic field. So you can see here that we can have lasing in blue and no lasing by just changing the magnetic field of our device. And we have isolation of almost 10 dB. Again, I said, regardless of the shape of the boundary, we should be able to have lasing of the system. So what we did is we use the same dimension that we have in the previous device without changing anything, the same fabrication method. And you can see here, when we just change the shape of the device, with the same dimension, we still have lasing at the edge, which is for the first time was done because there is no laser that you can deform the cavity and still have lasing. And you can see here we have isolation of 11 dB in both sides. So again, we said, okay, since you can really shrink the shape without losing any functionalities, we can take an arbitrary shape of the laser, which means that you can design, for example, a chip, and you don't think about your laser. At the end, you look at what is left as a shape inside your laser, and you can design this type of laser that can emit inside. And we did it with arbitrary shape, without magnetic field, no lasing. With magnetic field, we have edge state, and the mode is here. And we have also isolation of 11 dB. So this shows that we can really design geometrical independent cavities without losing any functionalities. We can shrink the chip space without losing the functionalities. It is type isolated source, which means you don't need any additional component to avoid backscattering the light, such as an isolator. And of course, this can be used to design a better functionalities. And this work was selected as the top 10 breakthrough by Physics World in 2017. By using the same physics, also we can generate what we call orbital angular momentum, which is the structured light. So we can multiplex the same design that we did before by putting it in a circular shape. We can multiplex multiple lasers that can emit orbital angular momentum with different topological charge that can use for imaging, but that can be used also for communication. So this brings me to the second part of my talk, where I would like to talk about singularities in non-Hermitian system. So I would like to start always by the physics behind. So I would like to compare Hermitian and non-Hermitian system. we know most of the physical systems that we know in general are open in nature, which means that energy can flow in and out and exchange with the environment either by radiation or absorption, which is in contrast with the closed system where energy stays conserved inside. But one of the fundamental difference between Hermitian and non-Hermitian system is the fact that for Hermitian system, the mode that you have inside for Hermitian system will always couple, and the eigenvalue of those modes are always real. And for non-Hermitian system, the eigenvalue is in general complex. So I will explain it in more detail in the next few slides. So in the last decade, many have sought to bridge the physics of open and closed system. This underlines one of the fundamental differences between Hermitian and non-Hermitian system, their singularities. When you have a Hermitian system, you have two modes inside, they always couple to induce the singularities that we call dibolic point. But when you have non-Hermitian system, you can have two optical modes that can couple to induce both dibolic point and exceptional point. And today we are interested on exceptional point, and I will go to the next slide to tell you why exceptional point is exceptional. So just a brief explanation again for the physics of exceptional point. So it is a non-Hermitian complex matrix. When you operate at exceptional point, what happens is your eigenvalue and your eigenstate will coalesce. So I would like here to use a 2x2 non-Hermitian matrix and use two-ring resonator to explain in a very simple way how we can reach such exceptional point. So you have two-ring resonator with different size. We know if you want to determine the resonant frequency of the ring resonator is always depend on the size of the ring. We know also the coupling coefficient, which is G here, between the two rings is depend on the distance that you will put between them. Since it is non-Hermitian system, you have both real part and imaginary part. So the idea here is to look at how imaginary part and real part will behave as function of the radius and d, which is the distance between the two ring resonator. So if we calculate that real part of the eigenvalue and imaginary part of eigenvalue, you will see here a very nice Riemann shape where you have two modes that have avoid crossing. So you have one optical mode here on top, one optical mode on bottom. But in the same position, if you look at the imaginary part, the two modes are touching each other. And the opposite is happening here between these two parts. If you look at this plot very carefully, there is only a single point where both real part and imaginary part of the two modes are exactly the same. This is what we call exceptional point. And why are we interested on exceptional point? Because it was used for different applications in different frequency range, from acoustic to microwave, in optics using dielectric waveguide. But the question that we ask ourselves as usual when we work in a project, what is done and what is left, is why no one did exceptional point using a plasmonic, which means metal. That's because the metal can confine light in a very tiny and small space, which is what we call subwavelength confinement. So we ask ourselves why people didn't do it. But before responding to why we need exceptional point at subwavelength scale, I would like to show why we need, what is exceptional point in a different way. So here, exceptional point is singularity that is very important for sensing. But if you look at here, what I would like to show here is the comparison between dibolic point and exceptional point. So another simple definition is when you have two optical modes that have same resonant frequency, but their line widths are different, this is what we call dibolic point, to make it very simple. So when you perturb with this mode, if I talk about perturbation, I say epsilon. Epsilon means you have two modes that are at same resonant frequency, you change the refractive index, or you change the concentration of any analyte you want to sense. What will happen? The two optical modes will split. And in order to determine the sensitivity of your sensor is to calculate how much it will split. But this splitting is always linear to the perturbation. So when you increase your perturbation, your splitting will increase. However, when you operate at exceptional point, which is very interesting, is you will have the same behavior, but exceptional point again is when lambda1 and lambda2 are exactly the same, but their line widths are different. So when you perturb that mode, which means that you change the concentration in the system, the two modes will split. But the way they split is square root, which is different to any standard sensor that you can find in the literature. Always will have a linear behavior, but this one will have a square root, which means that the splitting will be easier to detect because it is large, which will increase the sensitivity of your sensor. And then, again, I said if you have two modes, you have square root behavior. How about if you have three modes, you will have cubic root behavior. If you have n modes that you put together at exceptional point, you will have n root behavior, which means that if you use an exceptional point as a sensor, you can enhance the sensitivity compared to any existing sensor. Again, why subwavelengths? We know plasmonic system can confine light at subwavelength scale. So the idea here is to combine subwavelength scale confinement of the light and the enhancement of exceptional point so that you can have a new type of sensor that can detect a very small analyte. And that is what I would show in the coming slide. So how we did that? Again, the physics behind. We pair two metal bar, we put them next to each other. So we will have two modes of opposite symmetry, what we call symmetric mode that is associated with electrical dipole, and anti-symmetric mode associated with magnetic dipole. So the symmetric mode, you see, you have plus charge and plus here, which have a repulsive character, and the anti-symmetric mode, you have minus and plus. So what we will do here is we will shift one metal bar respect to the others and see how the two modes will behave. So you can see here, you have plus on top, plus on bottom. When you shift one bar respect to the one on bottom, the repulsive characters that you have here, which show plus and plus, will weaken because plus will be closer to minus. And the opposite will happen to the anti-symmetric mode. It was minus and plus, and it will become minus and minus, it become repulsive. So the symmetric mode that was in the high frequency will go to lower frequency, and the anti-symmetric mode that was in the lower frequency will go to higher frequency. And you can see here, when we change the value of dx, which is the offset between two metal bars, you can see that the two modes will get closer, and at some point they will cross. And this is what we show here. And in the beginning, to define exceptional point, I said we need two modes that have same resonant frequency. And you can see here, we already showed that they have two same resonant frequency. So what is left is to be able to have the same line width. That means the bandwidth of the mode, the line width of the mode should be exactly the same. And to do that, we select another physical parameters, which is py, the periodicity perpendicular to the length of the bar. And you can see here, this value or these parameters can change both resonant frequency and loss rate. So we were happy by identifying the two physical parameters to reach exceptional point. And we put the first configuration, which is two metal bars, one on top, one on bottom in a box of dielectric. And we can see here in the resonant frequencies, the two modes are crossing, avoid crossing on the opposite side, which is promising. But if you look at the loss rate, the two modes are completely different. They don't cross. So we know that we have all requirement here, but we couldn't reach exceptional point. And why we couldn't reach exceptional point here? Because we use two modes of opposite symmetry. And those two modes of opposite symmetry, their loss rate are so different that you cannot put them very close to each other. So how we can solve this problem is by breaking the symmetry. How we break the symmetry is we shorten one bar so that the two modes, their loss rate will be close. And when you perturb them with any physical parameters, you can have crossing and avoid crossing in this case. So this is what we did. And we show that the red mode here and the blue mode have avoid crossing on one side and crossing on the opposite. And in the imaginary part, the opposite behavior is happening. And in this nice plot, there is only a single point where both real part and imaginary part are the same. This is what we call exceptional. So we prove for the first time that we can have exceptional point at subwavelength scale. But now the question is, we want to use such exceptional point to make a sensor. But if you look at the proposed platform here, is inside a dielectric, which means that if I have any other light I want to sense, it cannot be in contact with any metal bar here, which means that this configuration that I have cannot be used for sensing. So we have to break the symmetry in different way. If you look at the two metal bar here, you will say, oh, the two metal bar have the same size. So you don't break the symmetry, they are exactly the same. But if you look at one of the bar is inside a polymer, and this polymer refractive index is higher than the refractive index on the gold bar, which is in air, which is as if that the two metal bar, optically, they don't have the same size. So this is the way we break the symmetry. And why we choose this configuration is because one of the top bar can be used for sensing. So you can functionalize the top of the bar and look at the concentration. And again, we show the behavior. Red mode and blue mode are opposite symmetry cross here, and the opposite is happening here, and we have exceptional point. Then we said, okay, since exceptional point can give square root behavior, how about verifying that the exceptional point that we design can give a square root behavior? So we change the refractive, and we put a cladding on top of the metal bar, and we change the refractive index. You can see that we have this red square root behavior, and diabolic point is linear behavior. To verify this slope are 1/2 and 1, we plot the log scale. So the diabolic point is slope of 1, exceptional point is 1/2. So then we propose how we fabricate the structure, because it's always good to have the physics behind to make the design, but after you have to go to the next step, which consists of the fabrication, which is done in a clean room. So this is the main steps of the fabrication. We have e-beam lithography here by putting the e-beam resist. We have metal deposition, and we have liftoff. And the next step will be to add another layer to repeat the same process to have the multi-layer of the structure. This is the proposed platform. As you can see here, we have array of metal bar on top, and the bar that the metal that we use here is gold, and the second one is embedded in a dielectric, which is SU8. And then we use this is the SEM image of the fabricated structure. So to make sure the dimensions that we use for simulation correspond to the fabricated structure. So what we did is we use the dual beam FIB and SEM, and we make a cross section, and we can verify the geometrical parameters to make sure that they match the design parameters. And then we do the optical characterization. It is very challenging to map the whole plot here, but the easier way is to look at any time you have exceptional point, you will have crossing on one side and avoid crossing on the opposite side. So we said, if we verify that, we know we reach exceptional point. So we compare numerical simulation here and experiment. And you can see here on the real part, we have crossing, and imaginary part, we have avoid crossing. We choose another parameters, which is PY higher than the PY of exceptional point, and the opposite is happening. Red mode and blue mode are separate in real part, and in imaginary part, there are crossing. And we compare numerical simulation and experiment, and we have a very good agreement. So after we show that we can have exceptional point, of course, we show it for the first time in a plasmonic system, but we want to make it useful, which is using it to sense something that have that are useful. So we use the IgG, which is one of the most common type of antibodies that you can find in blood circulation. And knowing the level of IgG or the concentration of IgG is very important in healthcare. So what we did here, this is the flow chart, how we functionalize our system, is we have a metal bar on top. This is the proposed platform. We saturate it with the linker, and this linker will capture the antibody antibonding, which will capture the anti-mouse IgGs that we will use for different concentration, and see if our device can perform better than existing devices. So this is the plot of the how our device works. We have the concentration of the IgG, and we have the delta W, which is the frequency splitting that I explained at the beginning. And we compare the two types of sensor, diabolic point and exceptional point. So surprisingly, when you start on the top, you can see that diabolic point perform better than exceptional point. Of course, exceptional point operate always better in a regime where your concentration is very small. So we progressively decrease the concentration, and you can see here that by changing the concentration, you see the difference is getting lower, and at 1000, exceptional point become better than diabolic point, and it would go up to 100 attomolar. And then we reach what we call linker limit. So how we explain that limit? If you look at the system, on top we put a linker. And anytime you design your system and after you add a linker, you will induce a shift at least of 5 terahertz. So any concentration that we have that cannot induce a shift more than 5 terahertz will be considered our linker limit. Of course, this problem can be easily solved by considering the linker in our design so that we will not have this same problem. And then we show that we can have, again, square root behavior and linear behavior with diabolic point. And what is interesting here is by using exceptional point, we can detect 15 × 10⁻⁹ nanogram per milliliter, which is almost 300 times better than the state of the art. So this shows the motivation why we use exceptional point for sensor, because we did it for the first time at sub-wavelength scale, but we also show that it can really be better than the state of the art in terms of detection. So this brings me to the second part, the end of the second part of the talk, where we show exceptional point at sub-wavelength scale. And we also enhance attomolar immunoassay detection using this plasmonic platform. So now I will go to the last part, which will be mostly for imaging and why it is important. I guess most of the things I talk about today is related to laser detector, but imaging is something that people may be more interested to. So I just would like to start this part by showing one of the more fundamental discovery of Newton, which consists of the decomposition of the white light source using prism. So you can see when light comes through a prism, you will split it in different color, which is different wavelengths. But this is the most problematic, this is the biggest problem that people in imaging want to solve, because we want to have all wavelengths coming at the same time, at the same position, which is completely different to when you want to split the wavelengths. So how people are solving that problem? When you have a white light source going to the microscope, you want to have the same focal point with different wavelengths. People are using multiple elements. So you can see here, you can combine different lenses that have different opposite function. That is like doublet lens. You can use a lens with opposite dispersion. But if you look at the system so far, it is very bulky, because you always have to combine multiple lenses to be able to focus light at the same position, at the same focal point with different wavelengths coming. But again, due to the context of miniaturization that I mentioned at the beginning, we want to shrink the size of any optical element that we want to use. So meta-surface was proposed because it is ultra thin, it is flat, it is tunable, it is multifunctional to solve this problem. So I want to just to highlight some work that has been done before our work, that showing that they can have a bandwidth 400 to 660 nanometers with the efficiency of 40%, as a work 20% and 50%. But when you look at all these works here, what you will realize is very challenging to combine high efficiency and broad bandwidth at the same time, even though meta-surface is bringing a new generation of metalens. So now, again, we ask ourselves, can we make a new device, new meta-surface that can have high efficiency and high bandwidth at the same time? So before going to that, I would like to go to what is the requirement to have a broadband metalens, a metalens that work for different wavelengths. So let's consider here's the schematic I'm showing here. We have a glass substrate and we put different particles. Light is coming from left to right. You can see here, this is the focal point. When light goes through this system, we want to focus at this red point. what will happen is if you choose the middle of the lens as your reference and you calculate the phase that you need to bend the light at the focal point, what will happen is if you look at the equation, very simple equation, this is the center, the phase at different position minus the phase at 0 will give you the phase at different position in the lens. This is given by this equation where this is the frequency and this is the focal point, this is the size of the lens. So if you look at very carefully this equation, what you will see is your phase that you need at different position to bend your light towards the focal point is always linear to the frequency, which is the first requirement. If you want to make a lens, you have to know the requirement. One of the first requirement is knowing that the phase is always linear to the frequencies that you want to work with. The second condition is at different position of the lens, the way you will bend light is different. So the slope are different at different position of the light. So now, after having those two requirements, we said, what do we need to meet these two requirements and have a lens that can be broadband, but at the same time have high frequency? We said, let's choose a new type of particles. So these particles, why it is interested is we have circle in the middle, which is 1 degree of freedom that we can use to control the parameters. We have the cross, which we can control the length, but we can also control the width. So we have 3 parameters to fulfill 2 requirements, which is linear phase and different slope. The other requirement is to have a material that can be transparent from visible to the eye. So we choose to work with titanium dioxide, which have very high reflective index, and it is transparent. There is no loss from visible to the eye. And then we start designing our system. We said, let's start with the cross. In one, we have a cross, like we just have 2 rectangles that cross. And after we decrease the size of the width until we reach second particle, which is 2, because in this distance, we always want to have the right slope at different position. What set our limitation here is the fabrication, because anytime you want to design something, you want to be able to fabricate it. Since the thickness that we use here is 350, we choose 70 nanometers, 80 nanometers as the width, so that the aspect ratio is around 4, so that the fabrication will be easy to be done. So we stop at 2, and we said, what parameters can we change now? We go here, we reduce the length of the bars, and we add cylinders in the middle. And we start shrinking the size of the cylinders until we reach this last cross. So these 4 elements will be the elements that we will use at different positions in the lens in order to bend the light at the focal point. So this is the proposed structure. You know, when light is coming from bottom to top, the middle of the lens, you don't need to bend light because it's going directly to the focal point. But when you go towards the edge, you need more phase to bend the light at the focal point. So the shape of the structure is changing. And then we use nanofabrication, which consists here, the steps of the fabrication is e-beam lithography, ALD deposition, because we did atomic layer deposition in clean room, and we do liftoff. And you can see here the fabricated structure. This current lens that we will use to do characterization is like this. It looks like the same shape as we designed. And if you look at from the middle to the edge of the lens, you can see different size of particle and different shape of the particles, which will give you the right phase at the right position in order to bend the light at the focal point. That can be at different wavelengths or different frequency, but also with a high efficiency, because titanium dioxide, there is no loss in the system. And you can see here different position in the lens that is fabricated that we will use for the characterization. So in order to characterize it, since it is a broadband, we designed it to be broadband from 640 nanometer to 1.2. For easy to present, we choose few wavelengths from the beginning to the edge, and showing that when you look at here, the focal length is diffraction limited. And when you increase the wavelength, the size of the length is increasing. And we compare it with the theory that match very well. And then we want to see, because the idea was to have a focal length that is not moving, is exactly at the same position from the beginning of the design wavelength to the end. So we look at the focal length in black dot here, and you can see that the focal lengths remain almost the same on the whole range of wavelengths, which is from 640 to 1.2 micron. So we show, this is the experimental measurement. We show for the first time that this metalens can be very broad, which is almost octave bandwidth metalens. And this was selected as one of the most read paper in 2020, one of the top 50 papers. So after that, we have to characterize what I just said is the efficiency, because people were having hard time combining high efficiency and high bandwidth at the same time. So we choose different lengths with different sizes, and you can see that the efficiency is almost 70% in the entire bandwidth that we proposed the design. We look at the focal length for different diameter of the length, and the focal length remains the same in the entire bandwidth. And we calculate the full half width maximum to show that it is diffraction limited, and you can see that the three lenses are diffraction limited. So we show a successful demonstration of broadband achromatic metalens that can go from visible to the IR. And what is interesting here in terms of imaging here is that such lenses are very small. So you can go from 10 micron to 1 centimeter by 1 centimeter, which is easy to integrate, which can be used for in vivo imaging. You can imagine having a mouse having a lens on top of his head and doing the imaging at the same time is eating or behaving in a different way, so that you can have a living behavior of the mouse. And another platform that we demonstrated is how to use beam limiter, because usually when you do imaging, you don't want to have high power coming to the mouse that you want to do imaging. So you always want to control the power of the light. What we did here is we proposed a new type of lens that can be power limiter, because it can limit the power, but at the same time, you can use it as a lens. So we design a structure where the particles in the middle, we put what we call phase change material. This material, when the power of the light increase, it will absorb the light. When the power is normal, it is transparent and the light can go through. And which is vanadium dioxide, and we have silicon here. So you can see that when the lens operates at 25 degrees, which means that the power is low, because increasing the power will increase the heat in the system, which will increase the temperature and changes the behavior of the lens. So you can see here at 25 degrees, which is in lower power, you have a normal focusing on top here at different wavelengths. And when you increase the power of your system, your lens still focus, but is lower power. And we show that it can be also diffraction limited, all of them. So this can be also used to avoid heating in a biological tissue and so on. So just to summarize what I showed today in terms of devices, again, with the concept of miniaturization, we always need a system where you can have your source, which is the laser that can be very small, that you can densely pack in the system. You need a detector that is very sensitive, but you need optical element between them, which is lenses, which I show here also, that can go from visible to the IR. So for that, I would like to thank where I was postdocs, my previous group, thanks my group members here, and thank you for your attention. I would be happy to take any question.
I think everybody's probably pretty speechless. Like, this was amazing, phenomenal. So until we can see some questions come up in the chat, are there any questions coming up in the chat? I haven't seen anything just yet. So I'm intrigued with this. So it's not a lens like we would imagine a lens normally made of glass. It's a lens made of a metal that can actually see or transmit light that's wavelength of natural light all the way down to infrared. Is that what you're saying?
Yes, it was made by titanium dioxide, which is dielectric, but of course it can be made by metal, but metal will be more lossy, so it will absorb light, so your efficiency will be lower. But of course you can use any dielectric material that have higher refractive index than the glass, because your substrate will be always a glass and you will have the material on top. You can design it in the way that you can have even structured light, like the light with a different shape, generating multiple beams at the same time, generating bezel beam with lower side lobe. So there is a lot of degree of freedom that you can have using meta devices in compared to bulk lenses. And it is in addition to that, smaller and easier to integrate. And you can also do it in flexible material, which you can bend it in a curved shape and use it as well.
Wow, incredibly versatile.
Yeah.
Amazing. I was also intrigued actually at the biological sample that you showed with the antibodies. So you were suggesting, because of the ratio, if I've got this right, that the exceptional point gives you increased sensitivity because of the increased square root. Is that right?
Yes.
And
because
so
the way the two modes will split, like if the split is very small, it's very difficult to detect. But if the splitting is bigger, so square root is always bigger than linear in certain regime. So you will have always easy way to detect when you operate at exceptional point than just a normal mode.
So would that be possible then to detect, pretty much anything in blood? So you could detect viral particles in blood?
Exactly. You can use it for any type of things you want to detect. You have just to be able to functionalize the top of the bars or putting it on top of your sample. And you can do the detection by just shining light in your system.
Wow, mind-blowing. Amazing. Thank you.
Thank you.
Any other questions from the audience? Everybody's probably sitting back going, oh my goodness, oh my goodness. Well, I think we're almost at time at this point, haven't we?
I think so. Yeah, we do have another minute or two if there are any questions that want to be asked in the chat. But I will just quickly give a shout to our upcoming speakers. We have another presentation next week from Dr. LeBlanc, same time as this one. And following that, we have another presentation from Dr. Hinton. Dr. Hinton is in the audience. Thank you for joining us today. We look forward to your presentation in a couple weeks. And I know Dr. Hinton also has a presentation tomorrow with biotechniques. So you might want to check that out. That's been shared a lot in social media, and I can find the link to register for that in a moment.